Hi, everybody. I guess I'm gonna get us started. We only have like about 10 of us. We're getting a few more in. All right. So today's Tuesday, November 17th. We got a few more coming in. Awesome. So let me do a quick attendance check so I could just double check who we have here. Now, who is that? Sorry, I was looking at a profile picture. I see somebody has a I know that anime. So one where they like have like horror stories. And yeah, good morning everybody. I just don't see whose name is on there. But yeah, oh, it's Sophia G. I like that anime. All right, sorry about that. I got distracted. Okay. So, here's our attendance check question. If you can be guaranteed one thing in life besides money, what would it be? And it could be anything. It doesn't have to be material things or anything like that. You can be guaranteed one thing in life besides money, what would that be? Yeah, we got happiness, manga books. Wow, a lot of happiness, success. That's nice. That's nice so far. Ooh, pets. That's cute. Guaranteed pets. Yes. No, not to lose loved ones soon. That one's beautiful. Yeah, not to lose loved ones. That is so beautiful, y'all. There's like the class that has the least materialistic responses. Other ones are like materialistic. That's okay. I actually the first thing I thought of was like I want a house, I want a house for my family members, my dad. But then I was like, oh wait, like happiness, that's one that I probably would is better because just be happy in whatever situation you're in. You could be depressed in a house, college education, man, I know, right? Guaranteed that. Be guaranteed that I will be who I want to be career-wise. Career-wise. Yes, that one is very powerful. All right, y'all. So let's see who I have absent, and y'all can help me out. So I think I'm just missing Kaylin with a C. I am missing a few additional, but they have reached out about Wi-Fi issues, so I'll be sending the recording. And we do have some participation in class today. And I'll just figure out a way to get those students, you know, so they don't lose any credit and whatnot. But that's all I'm missing. Kaylin with a C. All right. Oh, okay. We got health or prosperity. All right. Thank you all so much for sharing. Let's get to it. So let's check out our agenda. So our agenda, it looks short, but it's actually, I don't know. I feel like number two, it's we already did our attendance check. Number two, interactive notes. I built in participation. And at the end of the interactive notes, I built in the Google Form exit ticket. And today we are collecting notes. So I'm already giving you that warning. Today we are collecting notes. So you want to make sure that you have your binder paper ready. Or if you're the type who does electronic notes, like you want to type out your notes and take screenshots, you could do that. You could just do it on a Google Doc as I'm going along. And you could feel free to go on Google Classroom and open up the slides and just take screenshots as well. So again, we are collecting notes today. We have two pause and participation points that will be that will be added for participation grade. And then lastly, async number 10 is due today. So that's just the overview of the agenda and overview of async work. Again, you want to make sure that you're doing the async work because it's essential practice so that you're not lost in the class if I'm doing like a skill or a routine. So just make sure on that. All right. And yes, Edgar, we will turn in our notes today. Let me actually show you all. Oops. Yeah, so I haven't really collected much notes, but I do think today's notes are important to make sure you all have down. So if you go to my Google Classroom, again, if you look at the stream, it's going to look confusing. But if you go to classwork, I have it all organized where we're in unit 2, week 2. And what we've had so far in this week, async 10. This one's due Thursday, and the notes collection is due today. So that one you want to do right after class, not wait till tonight because you might forget. And yay, we got Kaylin in with the C. Awesome. Oh, okay. Thank you for letting me. Yay, so we got 100% everybody here. Everyone here who doesn't have technical difficulties. All right. Welcome, welcome. So again, for those who just came in, today we will have notes collection. So as you can see here, there's 2 things that are due today. Async 10, and there's also notes collection, which could be super easy. Just turn it in right after class is done. And async number 10, it's on there. It's basically you practicing continuity from what we talked about yesterday. And we got 2 of you already turned that in. Yep, you want to make sure you kept up on the async work. That's why I'm giving you your reminders. All right, so let's get ready for our notes then. Again, you want to make sure you get this down. Okay, so today we're moving a bit on continuity, and we're going to kind of review instantaneous rates of change. Now, for those who were with me last year, it's kind of that was the unit we finished off with. If you remember last year's summative, it was about that falling boulder or something, and you were trying to find like what was its specific speed at some point in time. So that's what we're going to be kind of looking at. Now, it's okay if you don't remember that or last year if you checked out during distance learning because we're going to review it right here. So let's go ahead and title up our notes. It's called the instantaneous rate of change and the derivative. So that's the title. And our learning target is I can find the instantaneous rate of change of some traveling object and also make connections to its representation on a graph. So that's our learning target for today. And yes, these are on Google Classroom. That's correct. These slides are already on there. Yes. I could also point out to where they're at. But let's first get this down. Let me give you all, I don't know, 45 seconds on this slide. And you could simultaneously open up the slides from Google Classroom. That way you could just, that way you're not rushed if I'm moving on. All right, let me give us a few seconds to get this down. All right, 5 more seconds on this slide. All right, so that's our learning target. Let's jump into the first problem. So in order to talk about instant rate of change, we're going to review average rates of change. I think we did also do this module 1 as well, but I'm just going to again quickly review it. Let's imagine you have a ball that you threw, and its height over time in seconds is modeled with this right here, this upside down parabola. So basically, just imagine that you threw it right here. Let's just say that your hand is, I don't know, 2 meters above the ground, and you start to throw the ball. And this is its height over time in seconds, because we have seconds here and we have meters. And what we're going to do right now is review how to calculate the average rate of change, let's say between these 2 points here, the one in green and the one in blue. So we're going to review that. Now, average rate of change, basically, when you calculate that, it's like you're just calculating the slope between the 2 points. This right here is a note that you do want to get down. You don't have to write this word for word, just like the main essence. Given an accumulation graph, and this right here is an accumulation graph, anything like distance, beats, or any unit of measure. By beats, I mean like the amount of time your heart beats. That's just another unit. You could think of it as anything. You can find the average rate of change between any 2 points, and the line that connects these 2 points is called the secant line. Maybe y'all remember that, maybe not, but don't worry, we're gonna have some review on what the secant line looks like visually right now after we calculate the average rate of change. All right, first let me let y'all sketch the graph and sketch the little blurb up top. And I know secant line is a little bit cut off by the meters, but first let me let y'all sketch this and then we'll do our review calculations. All right, so hopefully you at least got a sketch down. I mean, it's just going to be an upside down parabola, and the points you want to put there are 1 comma 9, 2 comma 6. All right, let's review how to find the average rate of change. Then we're going to move up to the actual calculus of this. So example 1 should be straightforward. So of course, the slope between 2 points is the average rate of change. Y2 minus Y1 all over X2 minus X1. And I could go ahead and label the points for those who need it. So I think I'm going to make this X1, Y1, X2, Y2. All right, after labeling, I'm going to go ahead and plug in / substitute my values. So on the top, I have 6 minus 9. At the bottom, I have 2 minus 1. We go ahead and simplify it. So 6 minus 9 is -3. 2 minus 1 is +1. -3 divided by +1, we get a slope of -3. So the slope between these 2 points is -3. Now it's kind of hard for y'all to think about, like, what do you mean slope? There's no line here. Usually slope is connected to a line. So I'm going to right now draw what the secant line looks like, because what we just found was the slope of the secant line too. That's equivalent to the average rate of change. So here is the secant line. I just drew a line between those 2 points there in red. That's the secant line, and the slope of the secant line was -3. The slope of this is m equals -3. So just so y'all know, what we just found was an average rate of change. Not yet did we find instantaneous rate. We're going to review a little bit about what instantaneous means after y'all get this down. Let me give a few seconds on this part. Again, oh yeah, by the way, as y'all are getting this down, just notice how the slope is negative, which corresponds to the fact that the line is decreasing, which makes sense. The slope should be negative in this case. All right, so there's that one. Again, it's on Google Classroom in case you need to go back, but we're gonna take a look at the same graph, but now, before that, we're gonna review what does instantaneous rate of change mean? Because this right here was average rates. We're comfortable with average rates. It's just a slope between 2 points. But what is instantaneous? I'm going to go ahead and switch the slide. So what is the instantaneous rate of change? This should be a little bit of review, but For example, when you're driving a car, and when you're driving, there's that little speedometer that's right below there, and it tells you the speed that you're going at, right? So I want y'all to like use the chat right now. So just pause and think about this. When you're looking at that speedometer as you're driving, are you
Mhm.
looking at your instant speed or are you looking at an average speed? What do y'all think? And this right here is a question. So let's see. We have average. And then I have another one in the private chat that said instant. Oh, average. Does anyone else want to chime in? So we have maybe two who are saying we're looking at average. And then we have because it's presumed you're going X miles per hour. All right, we got Roxana who thinks it's an instant. Anyone else have any other chiming in on this? So we have average or instant. That's okay. So let's. Then we have more instance. And if I had more time, I would like to, we would discuss this and so forth. But because we don't have time, let me go ahead and give you all the answers. So what you're looking at, it's actually going to be wait, I see something in the chat. Yeah, so actually what you're looking at when you're driving is your exact speed at that moment in time. So actually what you're looking at is an instant. So that speedometer is not making calculations of your average speed each time. It's actually telling you exactly at that moment how fast you're going. So it's actually it's actually doing your instant speed when you're driving a car. That's how fast exactly you are going. And then we have instant. That's why my dad doesn't let me drive. That's okay. But yeah, so as you know, like if you like were to increase your speed, like you push down on the gas, your instant speed, like it's going up. It's telling you exactly like how fast you're going at that time. When you look, it's constantly changing because your instant speed will be constantly changing. It's not your average. But yeah, so that's just the reasons why. Thank you all for your input on that. But yeah, just make sure you circle or underline. It's your instant speed for this one. Number two. So the what is the instant rate of change? So instant rate of change is when you determine the rate of change at an exact instance or an exact point of time. For example, how fast am I going if I'm driving at exactly 10 seconds? Like after 10 seconds that I'm driving exactly at 10 seconds, what's my actual speed, not what's my average rate. So instant rate of change is when you determine the exact rate of change at an instant, a specific point in time. And then we got one more here for this, I think. Oops, yeah, sorry. Let me go back. Last bullet for this slide is we can estimate the instant rate of change. And maybe y'all remember this from last year. And if you don't, it's okay because I'm going to review it. We can actually do an estimate of what the instant rate of change is by taking a point and moving it closer to the point of interest. I should say of interest, not of interest. Take a point, move it closer to the point of interest. So what I mean by of interest is like if I want to know the exact speed at 2 seconds, I would keep two there, but then I move the other point around two, closer to two. You're going to see the examples, what I mean by that. It's actually easier when you have a visual. Let me leave this slide up for a bit so y'all can get this down. All right. Hopefully y'all got these three like informationals about what is the instant rate of change. Now let's try to do this third bullet where it says we can estimate the instant rate of change by taking a point, moving it closer. What do I mean by that? So let's look back at the same graph, but notice now that you know how that green point was more up? I moved it closer. I'm moving it closer to this point right here, 2 comma 6. So my goal here is I want to find out what the instant rate of change is at exactly x equals 2 seconds. I want to find out what is the instant rate of change here. So what I did is I'm going to estimate that by moving this point closer. So go ahead and you could do a little quick sketch of that. So this is the point I moved. This is the point that stayed the same. And in order to do our approximation, we're going to do the same thing. We're going to calculate the average rate of change by using the slope formula. So here's our handy dandy slope formula. It's going to come up like always in calculus. We're going to also build up more theorems from this slope formula. And we're going to go ahead and plug in our new values here. So change in y, so it's going to be 6 minus 6.75. And then at the bottom, we have 2 minus 1.9. So as we're doing like approximations, you're going to get decimals because, you're going to get closer and closer to the point. You're going to have to use decimal numbers. So if we do this here math, we should get that the slope now between these 2 points is going to be negative 0.75 divided by 0.1. You use a calculator because that's what I did. Divide this out, and now my slope is, instead of negative 3 as before, it's now negative 7. That's actually quite a difference. So now I have that the slope, or the instant rate of change right now between these 2 points is negative 7.5. And I should also add my units because this was meters and this was seconds. So my instant rate of change in this case is meters per sec. So the ball is traveling that fast when you take an average between here. So yeah, sorry about that. Y'all should put the units. I didn't have the units in example 1 because this right here is a speed. It's a rate that we're calculating. All right, cool. And then in the next example, we're going to again take that green point. We're going to move it even closer. And we're going to see how our instant rate of change is changing, or how the approximation of the instant rate of change is changing. All right, let me leave this for a few more seconds. I also, as y'all are getting this down, as my timer's going, but notice how the secant line is changing too. As my point was moving closer, how is that secant line, that red line right there, how is that changing over time as that point is moving closer to the 2 second mark, when x is 2 seconds, or to that point that says 2 comma 6. All right, I hope y'all at least got the sketch of this down. Let's go ahead and do one more. Let's just do one more because, it's enough to do 3 times for us to get the point. All right, let's move even closer. So I used, again, Desmos. All I did is here's the work already. Sorry, y'all. So I kind of decided, like, y'all kind of know the process, but I moved even closer. So this green dot is even closer. It's at 1.98 comma 6.158. All I did is I just graphed this parabola and I just moved this second point closer while keeping this point the same. So I plugged into the slope formula the same way we've been doing. I got this negative 0.158 divided by 0.02. And then notice how my slope is now negative 7.9. So, and it's going to be meters per second again, because that's our unit. This is meters. And our x-axis is seconds. So this is moving now at this speed. So it went from negative 3, then we moved the point closer, it went to negative 7, and then we moved the point even closer and we have negative 7.9 as the approximation of the instant rate of change at x equals, say, 2 seconds. And let's draw that secant line and see how it looks. It kind of looks like this. I tried my best to draw that line between the 2 points, but again, you want to keep in mind, how is this line changing over time? And like, which of these would make the best approximation for the instant rate of change at x equals 2? me also put that here. That's the thing we're doing, just so y'all know. I've been saying it, but I want to make sure I write it out. So again, we're trying to approximate the instant rate of change at x equals 2 seconds by moving the second point closer. So each time we were moving this green point closer and closer so that we can make a good approximation of what's the exact speed of this traveling ball at x equals 2 seconds. So that's our goal here. And maybe in your mind, you could like make an approximation, like which one of these would make more sense as the actual instant speed. Again, we are able to figure out the instant speed if we use calculus, but we're going to talk about that in a bit. Let me leave this up. And then we're going to do a pause and participation on a Google Doc after this point. But let me give you all some time to get this down. My timer went up, but I just added again my annotations. Again, just as a reminder, this red line is the secant line. Secant line connects any 2 points on your graph. The slope of the secant line, this M, is your average rate of change. So there's just some reminders I'm putting there. All right, let me know if anyone has any questions so far, by the way. All right. So don't be stressed out about the participation point. It's mostly very open. You don't have to be right. So let me first read it, and we're going to participate on a Google Doc, not in the chat for this portion. So questions to think about right now before I give you all the Google Doc. What happens to the secant line when the 2 points moved closer together? So if you look through example 1 through example 3 that we just did, what was the secant line doing? What was happening to the slope of that secant line? So over time, we calculated the slopes. What was happening to that? And how might the line look like if we were right on top of the point that we wanted? What if we just put the point right on top of 2 comma 6? Wouldn't that solve all our problems? So just some questions to think about. And here's where you're going to put your thoughts down. It's on this Google Doc. So this one, in this format, I'm able to track and give you credit for participation. Sometimes the chat not always saves what I need saved. So here's the Google Doc. I'm going to open it up with you to just kind of review the instructions. So again, I pasted the question up here so you have access to the question. I also went ahead and crookedly, because it's very hard, I don't know. I went ahead and took screenshots of example 1, example 2, example 3. And I also like put in the slopes there for you so you all can see how the slope was changing over time. Keep in mind the slope was meters per second was its units, and I forgot to put that in when I took my screenshots. So you're going to look at these pictures and you're going to try your best to answer this question. How you're going to get your credit is you're going to put your name or initials down here in these boxes. You're going to try to put your thoughts / ideas on answering those questions that are right up here. So again, you could put your initials if you don't want people looking at your name or knowing what you're writing, because I have Power School and I could give you credit by your initials as well. And we have 4 people in the document. So we should have 15 people. Thank you for those who are on the document. But for those there that are ready to answer those questions I posed for you, go ahead and put your name or initial and start putting down your thoughts or ideas. Good. We have 5, 6. 1, 2, 3, 4, 5, 6. 6. We need more of us in there. All right. Yay, we're all coming in. So again, this is for you to like pause and now think about the examples we were doing, just so that you can sense make what in the world, we're looking at. And all right, we have 5, 6, 7, 8, 9, 10. 10 of you are in here. Your name is up here. Yay, you're on the correct document. And we're still missing a few people. If you don't see your name, you want to get on in here. We got 11 that are in here. We're missing 4 more people. 4 more people need to get on this document. All right, we need now 3 more people. I'm just trying to see who's missing so I could prompt you with a message. We're missing 3 people. Let me see who's here. By the way, I also want to open it up so that if you are uncertain about how to answer the question, feel free to put notice or wonder. That's totally fine as well. I want to make sure that this is like low stress, so don't feel pressured that you need to know the answer to this. You can put a notice or wonder if you're stuck. Let's see who's not on the document. I think it's still, so we're still missing 3. If y'all can let me know if you're having issues getting on this document. Oh, okay. Thank you for messaging me privately. Okay, so for those who are having issues, you can go ahead and private message me your response via chat, and that's totally fine. So, for those of you who are unable to open the document, just private message me your thoughts on the chat, and that will be totally fine. Private message, or you could do it publicly. All right, I'll give a few more seconds because I see a lot of us are still writing. Awesome. I see some, I see full names. I see some initials. Awesome. Let me give you all a few more, maybe a minute more to get your thoughts down, and then we'll take a look at some of that. All right, let's finalize our thoughts. And it's okay as I'm looking through and you're still like finalizing your thoughts, that's fine. I'm just gonna just pick through some of these and see what's gonna lead us into our big ideas here. So let's see. All right, so we have some ideas and y'all are free to like take a look. All right, so we have the secant line became smaller right here, and the slope became bigger, so causing the slope to become bigger, showing the instantaneous speed at that specific point. I like that. says if the points were on top of each other, the line would just be the point. Since it's the only point, not two, which means no secant line. Okay, that's interesting. Okay, so you would not have a secant line. That's important. We have some great ideas here that Shannon's typing up. We'll get the more the points get closer to each other, we get a more accurate instantaneous point. Oh, I like this language. The secant line becomes steeper and steeper. Yes, that's what was happening, right? Like steeper in the negative direction. So steeper and steeper as the points move closer. The slope began to decrease. So indeed, like this, it's like you would think the slope is getting bigger, but because it was increasing in the negative direction, right? It was going from -3 down to -7.9. So you could think as the slope is decreasing because it's getting more negative. So I like that. The secant line becomes smaller. The slope becomes bigger. Yes, that's a great wonder and notice. I wonder if the secant line can have a positive output. That's a good wonder. Yep, we get something more exact when the points are closer. Yep, more steeper, more negative. Ooh, okay. Somebody remembers the shortcut way to say things. I think I used IROC last year, instantaneous rate of change. So as the points move closer, we see the secant line gives a better approximation of IROC, instantaneous rate of change. And then the slope got smaller. So then I wonder if like slope getting more negative is what we mean by getting smaller. The line would probably look completely different, maybe. So a lot of you are thinking and trying to think about like how would the line look when it's exactly there. Yep, and the slope got steeper. I love how y'all are noticing that. And then there's some thoughts on what would happen. I think the secant line will match up with the graph the closer we get to the point that we want. All right. So make sure y'all, if you did not get to put in your thoughts, please make sure that you do, because I will be giving credit for this. So if I move on from this, don't leave without actually putting your initials or your name, putting down your thoughts and ideas. You don't want to close this up if you haven't yet done that. All right, so I definitely want y'all to first think about this before I give you the answer. And wait, let's do some. Yes, okay, because I definitely wanted to call this one out, sorry. If we were right on top of the point we want, we would have a tangent line which shows the instantaneous point. So somebody remembers a little bit of tangent lines, and which is actually going to lead us near the end of this class into that big idea on what is a tangent line. So yay, yeah, happy Shannon that you brought that up. All right, so let's go on, y'all. Again, please make sure you put in your participation for that. Now let's go ahead and talk about what happens here. So let's go back to our notes, and now let's try to see what happens if we just put those 2 points right on top of each other. And that way we'll get the instant rate of change, and then I'll get this funny looking line that just, I mean, it should just go in through that point just once because there's only one point. So why don't we just put the 2 points on top of each other? Let's explore that option. So if that were the case, if it were the case that I do that, this one singular point would be both x1, y1, and it would also have to be x2, y2 because we only have 1 point. What can we do? I'm like, all right, let's go ahead and do what we've been doing. Let's calculate the average rate of change and we should get what we want. I use my slope formula. And let's plug in. So because the y's are the same, you get 6 minus 6 on top. Because the x's are the same, you're going to get 2 minus 2. Let's do some math. Well, of course, 6 minus 6 is 0. 2 minus 2 is 0. But y'all can even test this out. Use your phone, use a calculator. If you do 0 divided by 0, you're going to encounter a problem. And we did talk about this. Maybe some of you who did the Khan Academy homework remember, but I went ahead and did it on my phone. It says error. And the reason it says error is because you cannot divide by 0. Error. We can't divide by 0. So that's the problem that happens here. We can't just put the point right on top of each other. We're going to get an error and we won't get the exact instant rate of change. So that's why we were doing approximations. So that's super important. We cannot just put the points on top of each other because you get division by 0. Division by 0 means the 0 is right here at the bottom. It's perfectly fine to have 0 on top. Only when it's the bottom of the division sign that we have a problem. So let's make sure we get this down. So that's the why we can't do that, just in case if anyone was wondering. All right, let me give you all a few seconds to get this example there down. And then we're going to talk about, well, then what can we do to get the actual instant rate of change rather than just an approximation? All right, I hope you all got this one down. And again, yes, the slides are on Google Classroom, so you can always open that up. I think I saw like 2 or 3 of you on the slides. Okay, so now what are we to do? So we're gonna get technical here, and I did do this last year. So for some of you, this may be review. For some of you, this is new. So I'm gonna walk us all through it though as if it's new. All right, we're going to rename these coordinate points that we just started with. So these were the points we did in example 1. We're gonna rename them. This point right here, I'm gonna name x comma f of x. Input, output, right? X is your input, your output is y, which is f of x. So that's just renaming our point. We're kind of making it arbitrary is what I'm doing. This is the techie part, so just pay attention till we copy it down. Next, this point, we're going to rename as something else. So I'm going to imagine that from here, right, I'm going to move h amount of units to the right. So you're going to draw this arrow. See this red arrow down here? I'm going to move h units to the right of this green point down here horizontally. So I'm going to move over h units to get my second point. Because I'm moving h units, that means my x value is going to be x plus h. X plus h, see in red, plus h, I moved over h units, comma, that means my input is going to be take f of x, take x plus h, plug it into f, that's your output, f of x plus h. So these are my 2 points, I renamed them, and I'm doing this so that we can construct a new average rate of change formula, and we could do something where we can find the instantaneous rate of change or the instant rate of change. So let's please make sure we got this, get this down. Let me know if anyone has questions about how I relabeled these points. So if we have this set up, let me go ahead and relabel my points. So, okay, so this one's going to be x1, this one's going to be y1, this one's x2, this is y2. So then if I'm going to kind of recreate a new average rate of change formula, let's go ahead and plug in what we got. We know we have to do this minus this minus this at the bottom of the division sign. So let's do it. So the average rate of change formula becomes this: y2 minus y1 all over my x2 minus x1. For those who are taking a look at this, we can't really simplify the top. First off, this x plus h, it's trapped in these here parentheses, whatever f is. And down here, there is something we can cancel out. I don't know if y'all want to use the chat. What's something we could cancel out there at the denominator position? All right, we got Roxana says x. And Viviana, sorry, we had another one. possible x plus h. So let's see. Thank you for participating, y'all. So the thing that cancels out is what's the same here. So x minus x. X minus x is just 0. So this cancels out. So Roxana, you got that? And then, so then this therefore becomes this. This is our new average rate of change formula. And again, this happened because we renamed our points. And with this new formula, we're going to create the instant rate of change formula that we need. So make sure you get this down. Let me just pause here, and I'm also pausing for questions. And then Rosa, you said, and we find H. So usually, well, last year we did do we use this formula. You can. I mean, that is a thing you could do, actually. So last year when we used this formula, we actually did the deep calculations, which is going to be the next assignment that's due on Thursday, not the one that's due today. But y'all are going to review how to do those it was like a lengthy process, and I linked up videos and so forth. But you're going to be asked in your homework how to do this, and don't worry because I included a video step-by-step process. But after you all review how to do the long way to do it, I'm going to give you all shortcuts for how to find the instant rate of change after, we get some practice with the formal definition. All right, so this is the average rate of change formula. This is the new one. Let's go on to the next slide so we could now finally get what the instant rate of change is. So I don't know if you all thought about it, but we need limits. So when we had, sorry, let me go back. If this h becomes 0, that means this point would be right on top of this point. So what we're doing is we're going to take a limit, the limit as h approaches 0. H approaches, sorry, that's h the limit as h approaches 0. Because when this h becomes 0, this point will be right on top of this point. Because there's no horizontal distance between the 2 points. It'll be right on top of it. So what we need here to get the instant rate of change is a limit. So what we did is we simply put a limit as h approaches 0 right in front of this formula. And that's where this comes from. So let me just go back to it. Sorry, so y'all can copy it down, but I needed the picture. So the instantaneous rate of change definition is this formula right here. The limit as h approaches 0 of, and it's this average rate of change, f of x plus h minus f of x all over h. And let me give you a new definition. The instantaneous rate of change is also known as the derivative. So super important. Let's make sure we write this down. And again, some of you remember this from last year, but if you don't, that's okay, because we have some review. And our assignment, our next homework assignment will be review on this. And then we'll have some shortcuts after that. But definitely I want to kind of just build up, like, where does this formula come from and why? It's the concept of those 2 points moving closer and closer together is where this is actually coming from. That's why we have that limit right in front of the expression. All right. I hope y'all got down the definition and also the fact that this is also called something we call the derivative, the instant rate of change. It's also known as the derivative. Now then, how in the world is that? What do we need to know about the derivative? Let's write down some stuff. So the formal definition of the derivative is this, what I just showed you. And we have some new notation for it. We're going to use this probably in our next class. So the notation is this. We say this as f prime of x. It's like f with a little apostrophe and then x. That's how we would represent the derivative or the instant rate of change of a function. There's another one, not just this one, and both of these show up on the AP exam. There's this one, this is the prime notation, and then there's this one. I just call this one the ddx notation. How you read that is derivative with respect to x. I don't really know why. That's just with respect does not mean you have to give respect to x. It just means like, I don't know. Derivative with respect to x is how you would say that one. Or I just say d dx. All right, right after this part, we're gonna go ahead and have our Google form exit ticket. And that's gonna be our checkout and our second participation point. And again, feel free to ask any questions, but let me leave this one up right now. Let me grab the form. So for those of you who are done with the notes and just go ahead and get started, let me just grab the quiz. I didn't really get to talk about the tangent, but don't worry, I'll finish up with that. That's why I was very happy that Shannon brought that up, tangent line. Y'all can look at that if you're curious, but let me get you the exit ticket. And I'm gonna drop it in the chat. Here's our exit ticket. You wanna make sure you complete it. And let me put this back up. And in your exit ticket, it's all participation. You do not have to worry about being right. I just want to hear your thoughts. It's like, what did you get from this lesson? What's your understanding? Again, so this limit right here in front of our definition represents the 2 points getting closer. Limit represents the 2 points getting closer. Oops. This right here is your change in y. And the h represented the distance between the horizontal distance between the 2 points. Just so that we break down this formula. There we go. All right, so everyone should be on the exit ticket. You should be completing the exit ticket, and that's going to be our checkout today. Once you're done with it, you are free to head on out and enjoy your evening. Oh yeah, by the way, I will send out the video because 3 people are having difficulties. So I'll be sending out the recording, as well as the exit ticket if you need to review it and then still complete the exit ticket. Let me know. I'm happy to send it out. And by the way, once you're finished, if you could let me know in the private chat, and I'm happy to be like, all right, see ya. Yeah, and for those asking for the recording, it's gonna take an hour to upload, but it should send by 3 today. So I'll send it on Remind at 3. I hope y'all have me on Remind. It's at, let me just make sure everyone has the code. My Remind is going to be, because I have 12 of you, so I'm missing like 4 people in here. Yeah, so all you have to do is send a text to 81010. And it's going to be at AP Sedano. All right. Thanks for those who are messaging that you finished up.
Bye, Miss Adano.
Bye. Bye, Viviana. Thank you. Bye, Fernanda. Thank you. All right. Bye, Edgar. Thank you so much. All right. Bye. Bye, Shannon. See ya.